Hi, I'm Fraser, one of Dawson's PhD students, and I work on building automatic bug finding tools, more secure systems, and attack proof of concepts sometimes. I'm really excited to be giving this lecture today, and I'm here with a couple guests.
My name is Samuel. I work at Project Zero in Google, where I do vulnerability research and like exploit development and all kinds of security work.
Hi, I'm Riyad. I'm one of Dan's PhD students. I occasionally implement crypto and I occasionally break things too.
Thanks again to the guests. Now, you've already talked about buffer overflows and control flow hijacking. In other words, ways to exploit bugs. Here, I'll be talking about how to find these bugs in order to exploit them, with a special focus a little bit on the browser, because that's what I have the most background in. First, if you're an attacker in the wild, the easiest thing to do is just let other people find the bugs for you. This can be a little hard because security bug reports are closed. Only certain user accounts are able to see them. But commit messages and diffs like this one are visible in the browser codebase, which leads to situations like this, or like this, where people get a sense of the bug, and possibly by extension, a sense of how to attack it, just by reading Git logs. The main takeaway here is that Twitter is always watching, and that if you're an attacker, you can watch both logs and security Twitter too. But maybe reading a bunch of commits and tweets sounds like a lot of work, lots of scrolling, lots of reading, lots of outrage. One alternative is to hack directly into the browser bug database. That way you can build exploits for as of yet unpatched bugs. Unfortunately, this is going to be a ton more work than scrolling though, so another alternative is to base your exploits around known bugs that have been patched in new versions of the browser, but that still exist in earlier versions. People just don't update their software regularly. In fact, this recent paper finds that it can often take more than 2 weeks for people to update Chrome when a fix comes out. That's a long window of opportunity in which to attack their machines. Finally, another strategy is to look back through old bug reports, or even just through the source code, to identify buggy patterns manually. Then you can identify instances of that pattern that early fixes may have missed. Here's snippets from 2 bug reports we sent to PDFium sort of recently, and you'll notice that they're both basically identical. That's because the bugs themselves are also basically identical. And we'll come back to finding buggy patterns like this later. So switching gears a little bit, just to one question about bugs in the wild, are there any characteristics you notice when you're investigating some bugs that are getting actually exploited in the wild?
Yeah. So I think the one main lesson I've learned from looking at a couple of the in the wild bugs we've seen in the last years or months is that most of them are variants of other bugs, or at least like the kind of bug pattern that researchers submit to the vulnerability rewards programs and stuff like that. It's not like it didn't seem to be like completely entirely different classes of bugs. It's mostly been bug classes that are kind of well known, and it makes sense, right? I guess if you're an attacker, you probably just want like with least effort get a bug that works, right? And so the way to do it is probably you look at old bugs, you search for variants of these bugs, and then you find one maybe kind of quickly, and then you're done. And so it's probably not surprising, but this is, I guess, the one thing I found interesting from that.
That brings us to our first unofficial, unsanctioned bonus point opportunity. If you manually find a new browser security bug and have that bug confirmed, and then send me a PDF with the confirmation, you will receive an extremely impressive prize. The prize will be great. You should do this. Now let's move on to strategy 1.5 for finding exploitable bugs, which is just turn on compiler warnings. Sit with that for a moment, let it sink in. This is actually a common strategy for professional pen testers. Turn on all the warnings and often end up with something exploitable up front before doing any more complicated work. We're going to look at an example of using compiler warnings to find potential security issues. Specifically, let's look at the Apache web server, which is a frequent target for hackers. We're going to look at a roughly 10-year-old version of this software, though, and what we'll see is that the way we write security-critical code has evolved in correspondence with the kinds of warnings that compilers emit. We're going to start by building Apache from source using a modern C compiler and a reasonably conservative set of build flags. Ideally, we would use Wearer, which makes all warnings into errors, but unfortunately we can't do that here. Apache just won't build this way. Instead, we're going to just take a look at the resulting warnings as they go by. There's an interesting and slightly unfortunate point to note here, though. By default, most C compilers, including Clang and GCC, do not use conservative warning options. You have to turn on the warnings yourself. You should always do this. If your C code doesn't build with Wearer, Wall, and Wextra, that code is broken. Okay, so we see some warnings going by here. And when we scroll back to specific warnings, we're going to see a lot of issues with unsafe format strings. Format string vulnerabilities were a major issue starting roughly 2 decades ago, but they've become nearly extinct precisely because compilers can detect and warn about them. Indeed, if we build a modern version of Apache, we should expect far fewer format string warnings, or maybe even none at all. You can see, though, from looking at all these warnings, that they're a really, really good place to start if you're looking to attack a piece of software. But let's say you want to use a tool. The next easiest thing to do in most cases is to fire up a fuzzer, or automatic random tester. Given a program executable, fuzzers feed that executable a number of random or semi-random inputs. If the program ever crashes, they automatically report that crash to the user. This sounds pretty dumb, but it works extremely, extremely well in practice. Google finds fuzzers so valuable that they fuzz 24/7, continuously, on at least 25,000 machines. And as a result, their fuzzing infrastructure, OSS Fuzz, has found over 16,000 bugs in 250 different projects. Here's a summary of all the bugs OSS Fuzz found after fuzzing continuously for 5 months. Finally, anecdotally, the JIT compiler teams I've talked to at multiple browsers say they get the majority of their security bugs from fuzzing. Now that we've established how important fuzzers are, let's talk about how they actually work. And it's not just by feeding programs random garbage. There are different kinds of fuzzers. Mutation-based fuzzers mutate known valid inputs to make new inputs to the program under test. Generation-based fuzzers generate inputs from some specification. And finally, evolutionary fuzzers generate inputs in response to some observed program behavior, typically coverage. AFL is the most popular fuzzer right now, and it's an evolutionary/mutational fuzzer that works based on program coverage. This means that typically one has to instrument the program under test so that AFL can measure program behavior and program coverage. This is AFL's documentation explaining its fuzzing algorithm, but we're going to slow it down a little bit. Step 0 is to give the fuzzer a set of good quality test cases for the program under test. Good quality here means that the test cases represent many valid program inputs. So, for example, given the SQLite database, valid SQL programs is better than giving it random strings of numbers. Bad quality seed inputs lead to bad fuzzer performance, since the fuzzer operates by mutating seed inputs. Now the fuzzer takes the first input in its set of seed test cases, and it minimizes that test case to the smallest version that doesn't cause a change in program behavior. This makes future errors easier to triage since there's fundamentally less content that could be causing the crash. Then it mutates the minimized test case multiple times. AFL loops through each new mutation and feeds the program each one. If the new mutation causes a program to explore a new path, AFL adds that test case to the seed queue. Otherwise, it discards the test case as redundant. Finally, it returns to the queue and repeats the entire process with a new seed test case. This doesn't mean that we're using AFL to feed inputs to the entire browser. Rather, you can use fuzzers to test browser components individually using the libfuzzer architecture, say, to set up a harness for each component. Which brings us to our next bonus point opportunity. If you create a fuzz harness for a currently unfuzzed browser component, and then effectively fuzz that component, you can email me to receive another even better prize. Can you tell me a little about fuzzers that you use and how they help you, and then maybe a bit about fuzzers you have made?
Yeah, sure. So I think I actually start maybe the other way. So fuzzers I use, one of the biggest one, I have this JavaScript fuzzer, which I wrote myself, Fusilli. And I use that a lot, I used it a lot. I'm going to use it again very soon. And it's pretty targeted, but it's like specific for JavaScript engines, doesn't work very generically. So that's one of the biggest ones. I also do like kind of ad hoc fuzzing with, for example, AFL or HomeFuzz is one project I used a lot. And then I kind of tend to modify it a bit for whatever I currently need, right? So like I recently did some closed source fuzzing project, and I had to do some like changes to things and like my own like guidance fuzzing support. So it's not like I just take a tool that exists and run it. It's mostly like I take something that I can change and make it do what I want. Yeah.
So like, what's a concrete example of some kind of change you might have to make?
Mm-hmm. So I think one of the things is that for like closed source fuzzing, I needed some kind of coverage guidance. And so I wrote something that would give me coverage guidance and then plugged it into HomeFuzz. And then it like, I reused most of HomeFuzz, but wrote my own coverage guidance. Yeah.
Great. And then can you tell everyone a little bit about how Fusilli works?
Sure. So the rough idea is like for fuzzing JavaScript, you want syntactical correctness, but you also want like semantical correctness a bit at least. So like you want the generated code to be mostly somewhat correct and so it doesn't throw exceptions all the time. And so the idea behind Fusilli is it has its own intermediate language called FuzzIL for sure, of course. And it kind of knows what this IL is or does, right? So there's like an instruction to load a property and there's an instruction to call a method and stuff like that. And then it knows how to mutate programs written in this language. And so it can like take two programs and like merge them together in different ways and stuff like that. So it kind of has a sense of what I guess what a program does and like how to work with these operations. Yeah, I think that's the very short version of how it works.
Do you find that your JavaScript fuzzer mostly it's hitting asserts and that's how you know?
Exactly, yeah. I think like 80 to 90% of the bugs I find are like debug assertions, which is exactly that, right? It's like code that makes sure that some state is sane much or way before it would cause memory corruption. And so I think it's kind of natural that this is what I end up finding.
So it sounds like fuzzers do a really good job, but there's still one problem. Not all bugs lead to a crash. Remember from this picture that we need a crash in order to know if we've hit a bug. But sometimes programs can of course be wrong and still just not crash. Consider this out of bounds right that, with most compilers, won't corrupt program memory in a way that manifests as a crash. We'll never know about this, even if the fuzzer hits this bug. That's where dynamic checkers like sanitizers come in. Dynamic tools find bugs in programs as those programs execute. Most of you have probably used Valgrind, a tool that, among other things, detects memory errors in running programs. In modern browser bug finding, fuzzers run on programs built with a dynamic sanitizer, which detects certain kinds of errors at runtime. The Clang compiler, for example, comes with a bunch of different sanitizers. ASAN, which finds memory errors like use after freeze and buffer overflows, UBSAN, which finds undefined behavior like bit shifts by negative numbers, ThreadSAN, which detects race conditions, and MemSAN, which finds uses of uninitialized memory. Let's zoom in on ASAN to understand how sanitizers work. At a high level, ASAN works by transforming all memory accesses in the program so that they check for access validity. In other words, this becomes this, which reports any invalid access of adder to the user. So the obvious question is, how do we know if adder is valid? How do we implement that isValid call? Well, we implement isValid using something called shadow memory. Shadow memory is a copy of memory that can be bit precise and tracks metadata about normal memory. This metadata is information like, is a given bit usable, or has it already been freed? Is a given bit usable and initialized, or is it just uninitialized garbage? And more. Lots more. You can basically do anything with shadow memory. Let's see how you can use shadow memory to track whether or not memory has been freed. First, you can automatically replace each call to malloc. Now, in addition to its usual job, malloc sets the shadow bits at its address argument to be 1, the usable bit pattern. Next, you replace each call to free. In addition to its usual job, free sets the shadow bits at its address arguments to be 0, the freed bit pattern. Now, if the program ever touches a bit whose shadow bit is freed, ASAN can report a bug. Backing up, in this case, the isValid function will check if adder's shadow bits have already been set to freed. If so, it will report an error to the user.
So we're going to take a look at the Relic toolkit, which is a cryptographic library. And specifically what we're going to do is we're going to look at how we can use the address sanitizer to actually find a bug in Relic. And this is a real bug, not a huge one, but still a real bug. Okay, so here I've got Relic built with ASAN turned on. And it turns out that if we run this test harness, we will run into an issue with, here we go, with Relic's memory access. So what we've just done is, after running the test with address sanitizer turned on, address sanitizer has told us that there's a stack buffer overflow during execution. So when that happens, ASAN kills the program and reports to us exactly what happened. So first of all, it gives us a stack trace that tells us, you know, where in the execution we were running, and in particular, so this is the function that caused the issue. We're going to go take a look at the source for that program, for that function in a second. But first, let's read through the rest of the report. So ASAN is telling us that we've actually overwritten a variable that's in the stack frame of the caller. Right? You can see that ep mul reg imp is the stack frame in which the overwrite happened. And so we've overwritten the stack frame of our caller for bnrecreg, which is quite bad. And in particular, it's telling us that this variable reg is what's getting overflowed. So we heard a second ago about shadow memory, and indeed that is how ASAN is finding this kind of overflow. So ASAN tells us this is how it's laid out shadow memory, and this is sort of interesting. What ASAN is doing in order to detect overflows of stack variables, it actually spaces all the stack variables apart and then puts what it calls red zones, you can think of these as sort of guards, around all the stack variables. And then if any of the guards get written to or read from, then ASAN knows something has gone wrong, because we should never be writing, you know, into the guard or reading from the guard. So in this case, what we did was we accidentally wrote into an address that should have been a guard. So you can see here F3 corresponds to stack right red zone. So what that means is that's a guard that comes after a stack variable. And this is the point at which we've written it. So remember a moment ago we heard about, when we heard about shadow memory, what we heard was, well, you can sort of have 1 bit per byte of memory, and that sort of tells you something interesting, like, is this allocated or not? What ASAN is doing is slightly more complicated than that. Instead, it's using sort of special canary patterns to indicate, well, this is a red zone that comes before a variable, this is a red zone that comes after a variable, and in doing that, it's able to sort of diagnose what's going on in a more detailed way. So you can see here, it actually tells us it has all these different kinds of shadow values that it can place in memory. In this case, the only ones that we ran into were the left, mid, and right red zones, and you can see those here in the shadow memory layout. Okay, so let's take a look at the source code that caused this. In particular, we're going to look at these 2 files, relic bnrec and relic ep mul. Okay, so on the left we have bnrec, And we can see that the line that I've highlighted here, where we're sort of dereferencing this pointer that's an argument to the function, naf, that's where we're overwriting something in the caller's stack frame. And if we go back to the call site, which is right here, bnrecreg, we see that we're passing in, as the naf pointer, we're passing in this int8t array reg. And this is what we're writing one past the end of. So one thing that we might do is, well, what if we just make this bigger? Maybe we won't overwrite it anymore. So what if we just add, I don't know, let's add 2 bytes to it, right? And now let's recompile and see if we get the same error again. Okay, so that should be pretty quick. Okay, and now if we run the test, what we should see is that indeed we don't get the error anymore. So what this tells us is that somehow we're overwriting a buffer by sort of, it seems like a static amount, about a byte or two. It looks like what we need to do is maybe debug this algorithm and see why it's writing past the end of the array.
Moving on to a kind of related topic, sanitizers. Do you find that you're usually running some sort of sanitizer as you're running a fuzzer?
So it really depends on what I'm doing. I think it's kind of similar to like it's all kind of tools in your toolbox is how I like to think about it, right? So you have like your fuzzers, you have like sanitizers, you have reverse engineering tools, or even something like grep also. Sanitizers are definitely a part of that. They make sense when you you're trying to find bugs that don't directly crash, for example, right? So like one example is these heap out of bounds, right, by maybe a single byte or so, doesn't directly crash when you trigger it most of the time. But if you put in a sanitizer, it works really well. When I do fuzzing for JavaScript stuff, I tend to not use like these generic sanitizers because I mostly, like the bugs I find are kind of more abstract. It's not like the heap memory corruption or so, it's some kind of like inconsistency in the engine. What I kind of think is like there could be more, I guess, domain specific sanitizers, where like you, for this project or for this code base that you're fuzzing, you're looking at what is the bug, like what could a bug look like? And then you're like defining or writing code to trigger on these error conditions much earlier than like way before they cause memory corruption.
We can also look for bugs without running the program, using something called a static checker. Conceptually, static checkers look for buggy patterns in source code. And traditional static checkers are part of the standard compilation pipeline. You give the compile a source file, and it lexes and parses this file into a program representation like an abstract syntax tree, or AST. Then the checker examines the AST for errors, and if it finds any, it reports them as bugs to the user. There are many different industry and open source static checking tools, but we're going to look at an open source one called the Clang Static Analyzer, which offers a number of different checkers for properties from like null pointer dereferences to out-of-bounds reads and writes to uninitialized memory. Here's what you get when you run Firefox's default Clang checkers on the browser as of about a year ago. This is a summary of all the different kinds of bug reports, like here, having use after move, that's a C++ specific check. This is just looking for dead assignments, dead increments, etc. Then if you scroll down, there's a list of individual bug reports. And then finally, we can zoom in on just one bug report, and we'll be looking at an uninitialized memory report. Here's the first part of that report. It's in the RAPL function. In step 5, in this red box, you see that type is declared without being initialized. Then in step 6, type is passed to read value from PowerFile. It might get initialized in the function call, we don't know, so let's follow read value from PowerFile. Here's that function. And the final parameter, aout, is type from before, that thing that we don't want to be initialized. And indeed, in step, that's type. So in step 9 here, you see that read value from power file returns without initialing aout or type. So now we return to the calling function, and after read value from power file returns, the next line, step 11, uses type. But remember, type may not be initialized because it didn't get initialized here, and it definitely was possible to not get initialized in the read value from power file function. An attacker could use the uninitialized read to try and examine sensitive data from program memory or something like that. So it's really good that the static checker found this. Okay, and let's see how the static checker found it. So recall that the checker is going to walk over the program AST, keeping track of certain pieces of information. In this case, looking for uninitialized memory bugs, the main data structure is going to be a set of all uninitialized program variables. Anytime the checker encounters a variable declaration, it adds that variable to the uninitialized set. Anytime the checker encounters a variable initialization, it removes that variable from the uninitialized set. Now that we know what the checker is keeping track of, we can traverse the AST. Here's an abridged version of the AST for the bug, and this is our main data structure, the set of all uninitialized variables. In the first node, type is declared, so the checker adds it to the uninitialized set. Next, FP is declared, so the checker is going to add that to the set too. But FP is initialized later in this node, so the checker removes it from the set almost immediately. Now the checker has hit a branch point. Conceptually, from here on, it's going to have to keep track of two different uninitialized sets now, one for the true branch and one for the false branch. On the true branch, type is initialized, so the checker removes it from the set. On the false branch, though, nothing happens, so the set stays unchanged. Now the checker's arrived down here at this join point, and it has to join together the two sets of uninitialized variables, the one from the false branch and the one from the true branch. To be conservative, it should take the union of the set of uninitialized variables, which looks like this. And after the union operation, our main data structure still contains type, as you can see, because it's possibly uninitialized. The checker checks if type is used in this node and finds that it is. That's a possible uninitialized memory bug because type is being used, but it's in our set of possibly uninitialized variables. Static checking has deep roots in programming languages theory. The key point is that all static checking requires abstraction, since making statements like, "this program is guaranteed to halt," is known to be impossible. There are two ways we use abstraction in static checking. First, we abstract away program properties that our checker doesn't care about. In the uninitialized memory case, that means abstracting away everything except uninitializedness. Remember that the set of uninitialized variables was our main data structure before. The second way we abstract is in how we handle control flow. Since we know we can't say if a loop will terminate or not, the checking framework has to make choices about how it handles information flowing into and out of loops. As another example, think back to our uninitialized memory checker again. When it reached the join point of the if statement, it conservatively took the union of the true branch and the false branch on init sets. That was a conservative abstraction. Abstraction implies that, in the general case, a checker will always either over-report possible errors or under-report them. That is, it will either report bugs that aren't real, or it will miss real bugs, or both, which actually becomes important when you're using static checkers in the real world. Static checkers aren't really finding that much in modern browsers. The first reason is that many errors in browsers are caused by weird interactions between different browser components, or by invariants being unexpectedly violated. For example, during machine code generation in the JIT, maybe the code generator for a certain instruction uses the wrong register name, which is a real thing that has actually happened. It's possible to encode these higher-level sorts of logic bugs in a static checker, but it takes work, and standard static checking suites just look for language-level errors like use after free or null pointer dereference. The second reason is that static tools suffer from high false positive rates. If you're faced with a mountain of 400 errors and 10 are real, you're not going to be motivated to manually go through all those reports to figure out which are real and which are false. This means that, because of the high false positive rate, you may even miss some true positives. We recently had to comb through about 400 Clang and Semley bug reports, and we found that both had a pretty abysmal false positive rate with some checkers. And results like that make people ask questions like this. Finally, the last reason static checkers don't find that much is that they make people miserable and fill them with sense of hatred and dread. I say this as a static checking person, but going through hundreds of bug reports manually is still awful. Compare that to examining a fuzzer's crash reports, where you don't have to reason about anything. You just have to look at the report. Bittersweetly, we have reached our final bonus point opportunity. If you create a new Clang static checker that looks for some high-level buggy pattern in a browser, and then if you submit that static checker to this program, you can email me and receive the very best prize yet. You should really do this one. And again, this is the bounty program you're submitting to. Static analysis tools. Any thoughts here?
So sure. I actually don't use much, I guess, in terms of at least automatic static analysis myself, or at least not yet. I think, again, it's like one of these tools in your toolbox, right? And I think that, like, I guess at least the way I see it, it should mostly support you in like whatever you're trying to do, right? And so often this ends up being like you're looking for some bug pattern in some complex code base, right? And you want to find possible instances of this bug by, I don't know, looking for data, specific data, so patterns or code pattern. I guess the reason why I haven't done much is, one, because of time. The other is, so far, mostly I've been doing well with just like cross-references. As I guess the most advanced thing I've been using, right? Like, where is this function being called? Okay, let's check out these 10 call sites. But yeah, I probably will use more static analysis eventually. And I think this is where it really shines, like supporting, like not replacing the I guess, researcher, right? Maybe I'm just saying that because I don't want to be replaced by a machine. But I do think it works best if it's really flexible and you can like target it to do what you want in very short amount of time.
Up until now, every strategy we've talked about has required having access to source code. We don't always have that, though. Think about most Apple or Windows software. So if we don't have a program's source code, but still need to attack it, we have a couple options. First, we can try and recover the source code from the program binary, typically using something called a disassembler or decompiler. The other option is to try and figure out how the binary works by observing how it executes. I'm not going to talk about this option now because we'll have a demo later. Let's instead talk about strategy 1, using a disassembler. Disassemblers turn the bits in an executable into human-readable instructions. How? Well, it can decode the bits the same way the processor does. Certain bit patterns correspond to certain instructions and their arguments. The processor manual actually has a table that tells you which patterns are which. Decompilers have a harder job. They have to turn assembly instructions into source code, which is pretty difficult because of compiler optimizations. Optimizations make it almost impossible to straightforwardly pattern match which sets of assembly instructions correspond to which source-level constructs. I'm about to show you an example of this, but keep in mind that my example is the simplest possible thing, and use it to imagine how complicated decompilation can actually get. To get a sense of how this works, let's look at this simple program, foo. What foo does is tests its input integer to see if it's greater than 0, and to see if it's divisible by 2. So we can compile this and look at the LVM that the compiler, LVMIR that the compiler produces. LVMIR is something that's kind of close to assembly. So okay, here's foo, and we have both those tests we were expecting. We have this comparison and branch, so seeing if the input is greater than 0, and then we have this divisible by 2 test using the srm instruction. So yeah, you can see how it would be pretty easy to go from this LVMIR back to the source. But now let's try compiling foo with like some actually pretty aggressive compiler optimizations, but we didn't have any before, so this is going to be pretty different. Let's look at foo again, and wow, that really changed things, right? This looks totally different. So what's going on here? We have the comparison against 0, and then they've turned the mod, which was an srem, into this and then compare. Because that's a lot faster to see if it's divisible by 2. Then they've also gotten rid of the branches, because those are pretty slow also, and instead they're just anding together the two conditions, and because we're returning a 1 or a 0, they can just extend that result and return it. So they've replaced multiple branches and an srem, all stuff that made it really easy to go from the LVMIR back to foo. To deal with the optimization problem, decompilers use complicated compiler-specific heuristics to recover source code, and even these sometimes fail. Another difficulty for decompilers is packing, or hiding program code and then reassembling it at runtime. Some proprietary systems do this, but so can, say, malware, in order to avoid detection. That's all I'm going to say about recovering source code. Now, Riyadh is going to give you an example of how to observe the behavior of a running program in order to get that program to do something different.
Let's take a look at how we might analyze and modify the behavior of a closed source commercial program. So I have a circuit simulator here, and I've got a license for it. And I can run it just fine. But if we look at the top of the output, what we see is actually my license is going to expire in a few months. So I might reasonably worry, what's going to happen when my license expires? Well, one thing we could do is find out. So, for example, we could just set the clock to something a little into the future. So now my machine thinks that it's April of 2021. And now if I try to run my simulation, oops, well, it tells me I'm not allowed to. Why? Well, it says it's expired. The license is expired. Okay, so one thing I could do, obviously, look, I can just change the date back, and maybe that would work. But this would be inconvenient if we were actually in April of 2021, because then I'd have to change my system clock every time I want to run this one program, which seems a little annoying. So we're going to do something a little different. So what I've done is I've started to write a little piece of code that's quite simple. I define a function called time, and the goal of this is to intercept whenever the program calls the time system call, to intercept it and to return a time that is far back in the past. So in particular, I'm going to return a time that's 10 to the 9 seconds since January 1970, which is something around September of 2001. Let's see what happens when we compile this. Okay, so now what we can do is we can run the simulator again, and this time we're going to preload this library interesting. Okay, so what we've done is we've LD preloaded this library, which catches the calls to time that this program makes. But now we get a different error. It says, bad date found on the running machine. Has system date been set back? Well, how would it know that? Let's investigate a little more. Before we do, I want to talk for 30 more seconds about LD preload. So what's going on here is the system's dynamic linker, when the binary runs, it says, I need this library and this library and this library, which the system has, and the dynamic linker at runtime provides sort of the memory addresses of the symbols that the program is requesting. So when we give LD preload on the command line, then what this tells the linker is, I have this other library that I'd like you to insert sort of at the head of the line whenever the program tries to do name resolution for a symbol. So in particular, in this case, when the program tries to resolve the name time to a symbol that's sort of presumably in libc, because we've LD preloaded, our symbol named time replaces the one from libc. but then our function called time actually goes and finds the real libc time and sort of calls that and then interposes on the result. So what we're doing here is we're playing a trick with the dynamic linker that lets us interpose between the program and the system. Okay, so let's get back to this question. How is it that the program is thinking that the date on the running machine is bad? One small clue we can already see is the error message is telling us, please check the file and directory creation dates in / and /etc. So it looks like what it's doing is looking for inconsistencies between the modify times of files in /etc and the date that the system clock returns, anticipating that we might have tried to set the clock back. So how do we suppose it's doing that? One way we can get a clue about what it's doing is by looking at the system calls that it's making. So I'm going to use a program called strace, which stands for system trace, that runs our program and records all of the system calls that it makes. So now, again, we get the same error message, but now we can look at the output of strace, and we can get an idea of what's going on. Okay, so if we look through this, well, okay, this is where it's sort of writing the error message at the end, but if we scroll up a little bit, what we see is the program is calling stat, which is a system call that gives information about a file. And it looks like what it's doing is statting every entry in etc, looking for future dated files. Okay, so again, this is a system call, which means we have the power to control what it returns to the program. And in particular, we can intercept the stat calls, and we can make them do whatever we want. So let's do that. I've actually written a little bit more of this program, and what we're doing here is it's a little bit of a mess, but basically we're intercepting all the ways that it could be calling stat, and then we're modifying the dates on the data structures that is coming back from stat, and that's what we're handing to the program. Okay, so now if we recompile this again, then we should be able to get it to run, and indeed it runs, and it thinks that the date is, as I said, sometime in 2001, because we've managed to fool it. So even though the program was trying to be a little bit clever in the way that it discovered what time it really is, since it fundamentally has to ask the system what time it is, we can fool the program, and we can keep running our software past its license's expiration date. Of course, you should not do this. This is for educational purposes only. Don't crack commercial software. It is morally wrong, and it will get you in trouble.
Up to now, we've talked about pretty commonly used bug-finding techniques. It's not hard to find real companies or vulnerability researchers using them. Now we're going to move on to a kind of bug checking that's very powerful, but also very slow and brittle and error-prone and generally hard to use, so very few people actually use it. It's called symbolic execution. Conceptually, symbolic execution statically determines program behavior over all possible inputs and all possible paths in a program. But wait, you say, isn't this impossible? Yes, it is, but you can try, and modern search tools for NP-complete problems are good enough now that you can actually get reasonable results sometimes. More on that later. To illustrate symbolic execution for everyone, I'm going to talk to you about a tool we recently developed for finding bugs in browser code. This tool is a combination of static analysis and symbolic execution. And, to recap, static checking identifies buggy patterns in source code, and symbolic execution conceptually runs programs over all possible paths and all possible values. Our approach uses static analysis to cheaply identify many potential error sites, and then it uses symbolic execution to jump directly to those error sites to expensively determine if they're real or not. This system requires programmers to write small static extensions and symbolic checkers to identify possible error sites. The static extensions are different from the static checkers we talked about earlier in this lecture, though, because they're much less conservative. Their whole job is just to guide powerful symbolic execution to useful parts of the codebase. If you want to use this tool in practice, this is what the workflow looks like. First, you provide it with an LLVMIR file of the code you want to check. This is LLVMIR that looks really similar to the code in the demo we saw before. Then you either write or use an existing static extension that looks for some buggy pattern to lead the symbolic phase towards. It outputs a number of suspicious paths within the codebase. Then, the user-written or user-provided symbolic phase tries to figure out if each suspicious path contains a bug. If so, it reports the bugs to the user. So let's walk through a bug this tool found, a high-severity vulnerability that was exploitable in SQLite on Chrome. This is a sort of anonymized text of the bug. The first key line here is this mymalloc call, which allocates some space for A using a custom allocation routine. The second line is the memset call, which initializes A. And the problem here is that mymalloc takes a 32-bit argument. This means that the multiplication in the mymalloc is a 32-bit multiplication, while the multiplication in the standard memset is 64 bits. This means that it's possible to craft very large inputs that will cause the 32-bit multiplication to wrap around to a small value, without causing the 64-bit multiplication to wrap. This leads to a very small allocation size for A, and a very large out-of-bounds write in that memset call off of A, right here. Now, let's talk a little about how, actually, before we do that, the key thing to notice here is that what symbolic execution is giving us is reasoning over all the possible values of these allocation and index sizes, unlike static checking, which just looks for buggy patterns. So this is a way more powerful technique that found this. And let's talk about how we found it. First, we wrote a static extension to identify cases where there's a dependency between an object's allocation size, in this case y, and its index size, in this case y-1. So the allocation size is y, index size is y-1. Since there's a dependency between those two, they both contain y, the static extension is going to mark this path as suspicious. And it does this, as we saw before, by walking through the AST and keeping track of information. On the first line, it saves the size of x to be y, and on the second, it saves the index size off of x to be y-1. At the end of the path, it sees that there's a dependency between y and y-1, so it marks this path as suspicious and sends it along to the symbolic execution phase. The symbolic execution phase has a more difficult job. It has to determine whether it is ever possible for the object's index size to be greater than its allocation size. In this case, if it's possible to craft values such that y-1 is greater than or equal to y, leading to an out-of-bounds write. If it determines that y-1 can be greater than y, it should report a bug to the user. But how does it possibly do this kind of value reasoning? Well, first, it translates each line of code in the program into a logical formula, something like the formula on this slide. Then, it can use something called an SMT solver to get a satisfying assignment to the formula. An assignment that makes the formula evaluate to be true. In this case, the SMT solver has given us assignment where A is true, and B is true, and C is true, so boom, the whole formula is true. Let's say we change the formula, though. Now there's no possible satisfying assignment, so the SMT solver returns unsat, no formula found. But how do we use this to actually find bugs? Well, we take the suspicious path and then translate it to a set of constraints. Then we'll have the checker write some more constraints to try and determine if the bug, in this case the out-of-bounds write, is actually possible. Finally, we'll query the SMT solver. If the bug is possible, it should give us an assignment for the program inputs that actually triggers the bug. And if not, it will just return unsat. So let's do this. First, the symbolic execution engine translates the first line into some constraints. Then the symbolic checker examines the line. There's no possible out-of-bounds index here, so it has nothing to do. Next, the symbolic engine translates the second line. Here we go, it's going to make like a temporary and some constraints for a pointer, and then generate some constraints on memory. Then it's the symbolic checker's turn to look at this line. This time, we're at an index, and we know the size of x and the index size of x. So we can craft a constraint asserting the error condition that y minus 1 is greater than or equal to y. This encodes an out-of-bounds right. And now we hit the SMT solver, and the SMT solver says that this out-of-bounds is completely possible. It gives us the y value 0, which indeed leads to an out-of-bounds excess. Before we finish, I want to quickly note that this is only possible because modern SMT solvers have great heuristics for solving NP-complete problems. It's a really cool area of research that combines theory and kind of dirty hacking, so I encourage you all to look into it. And with that, we are actually now done with today's technical content. We've gone over a lot of things that can be used for good or for evil, so I want to take a second here and encourage you really, please use them for good. Don't do evil things with this information. And let's end on a happier note by hearing from our Project Zero guest Samuel about his favorite bugs and exploit chains of all time. So this is my favorite question. What's your favorite bug?
Okay. Yeah, this is tough. So I don't think I really have a favorite bug. I think if I had to choose, what I probably would pick, but like maybe mostly just because I have positive memories associated with it, probably the one of my pwn to own exploit chains from like 2 years ago, which was like a JIT bug and then 2 logic bugs. So it was just a really nice chain. Like it was all stable. It's kind of clean, elegant code. It would run really fast. So this would probably be the one thing. Also because I really wanted to find a JIT bug for months or even a year or so, and this was the one, like the first one I guess I found. So it was kind of a highlight, really. And so the other thing is the other I would say is the iMessage bug I exploited last year. Mostly because it was like I was kind of skeptical that you could pull off these 0-click exploits in a good way, where like the target, you just really need the phone number and then you can like hack into the device without any interaction. And then eventually it worked, and I was pretty stunned that like I had managed to come up with this exploit that, does all of this in like 5 minutes.
That's awesome.
Yeah.
Can you describe the JIT bug from like the first part of the exploit chain?
Yeah. So let me think. So basically what's going on is the way the JIT works is it makes like assumptions about state. It like assumes something is going to be an integer or so, and then it puts in like guards or like type checks all over the place, where like it assumes something is an integer, but it's not guaranteed, so it has to put in some like type check. And so the one other thing it then tries to do is like figure out if there are redundant checks. If like it checks something as an int, and then a few lines further down, it again checks if it's an int and it's probably redundant. And so the bug here was that it thought one of these type checks was redundant and it would remove it. But actually in between the 2 checks, you could run some code that changed the type. And now you had a type confusion because the compiler would like take away this type check incorrectly and then assume that like this variable had a specific type. It didn't, and so you had a really cool type confusion bug.
And can you explain a little why type confusion bugs are cool and helpful?
So they probably are like maybe the most powerful bugs, I guess, you would find these days. Mostly, or at least if it's a good type confusion bug, mostly because you like get to kind of choose what to confuse stuff with. Like you can confuse this one object with a couple of other, or dozens or hundreds of other objects. And then it lets you build really powerful primitives. Like if you want to do memory read writes, you would like access some pointer field and then replace it with some other pointer, and then that would let you read and write stuff in memory. The other nice aspect is that tends to be really like reliably exploitable, because in like if you think alternatively of like heap out of bounds writes or so, you always need this heap layouting to work correctly, right? You're like overflowing from some chunk, you have to make sure the thing you want to overflow in is behind. With type confusions, you don't have that problem, because it's like you're confusing type A with B. Okay, there's no heap layouting necessary. It just works basically. And when it works, it's really reliable.